Alright, so we're going to look at the second derivative and points of inflection. So I'll put some prior knowledge in the description below, but lecture 37 about differentiation for specialist maths is probably a good one. There's also just a lot you need to understand about the big ideas of differentiation, so I'll put some links below. Key concepts we'll cover in this: the derivative, the second derivative I should say, we'll look at a visual demonstration, then we'll do stationary and non-stationary points of inflection, we'll look at the idea of concavity of a function, and then classifying points through derivative analysis. So let's jump into it. Let's just talk about the big idea of the second derivative. I don't think it's too tricky if you understand how the first derivative is calculated, but just as a reminder, let's imagine we've got some function f of x. And remember that the derivative is basically graphing the slope of a tangent line for all the same x values. So for example, if we've got this orange tangent, you can see at the x value of negative 4.19, the gradient is 0.43. And then so this point here corresponds to the gradient graph. And then so as we trace this tangent out, we can see that the blue line is now going to trace out another function. And interestingly, what we're going to be investigating in this lecture is sort of these interesting points, because you can see as it gets to the top there, the gradient goes to 0. And so that corresponds to an x-axis intercept on the derivative graph, which is now in blue. And hopefully you've seen this type of thing before. If you sketch it out, you can see the gradient is now negative, and then it's becoming positive again. And then it's going to become, it's going to go to 0, and then it's going to become positive again. So no surprises for guessing, hopefully, that the pink function is a cubic function, and then when you take the derivative, you get a quadratic function, which we have in blue there. So yeah, there's that. And then so the second derivative is basically just this idea that we just do the same thing on this new line. Now we put the tangent on this line and then trace that out. So now it's going to be in green, the derivative of this quadratic. So the slope is going to 0 there. So that corresponds to an x-axis intercept. And yeah, we sketch it out like this. And so the second derivative is just doing the first derivative again, right? So you end up with a situation like that, which I think looks pretty cool. And hopefully not too new to you. Okay, but what will be maybe a bit newer potentially is, taking sort of doing more in-depth analysis. So thinking about and interpreting what the second derivative means. So let's talk about that. Here is a complicated function in pink. Okay, we've got a lot going on, and we're going to talk about a few key concepts. One of the first key concepts we're going to talk about is what's called concavity. So you can see here we've got a little diagram. Basically, we say that a function is concave down if the tangent at a point on the curve is above it, and we say it's concave up if the tangent is below it. And so what that means for the first and for the second derivative rather is that it's concave down if the second derivative at some x value is less than 0, and it's concave up if the second derivative is greater than 0. So let's have a look at this instance here. We can see to begin with that this tangent line, and I encourage you to pause the video and think, is this concave up or concave down at the moment? But hopefully you've had a think. You can see that it's actually concave down at the moment. Okay, it's concave down because the tangent line is above the pink line at these points. Okay, once we get to this local maximum, I think you would agree that the derivative there is 0. The slope of that line there is 0. We have a local minimum over here as well, which corresponds to an x-axis intercept on the derivative graph. So in blue here, we have the derivative graph. And so, we slope it out, we go around with our function, and you can see in between here, and this is where it gets a bit tricky. If we think about this idea of concavity, it's concave up, still concave, it's concave down up to here. It's still concave down, but you would agree at some point it's going to become concave up, and that's right in the middle there. So there's a lot more we need to analyze. So you can see now, went from being above the pink line to being below the pink line now. So that point, I think you can probably guess, is right where that minimum is on the derivative graph. So we have a change in concavity there. So that means it's a point of inflection, and where the second derivative changes sign, because we've gone from concave down to concave up. Okay, and so yeah, you get this cool stuff going on. And similarly over here, you're going out here, you can see that it's concave down, and then it becomes concave up, and then it's concave up all the way to here. Okay, so if we just sort of step this out, we can see that this point here that we were describing is a non-stationary point of inflection. Okay, non-stationary because the first derivative, which we have in blue, is not zero at that point. So it's called non-stationary, but it is a point of inflection. Okay, and then if we were to graph the second derivative, you can see that the second derivative, if we've got it graphed here, changes sign at that non-stationary point of inflection. Okay, so we have that situation going on where these are non-stationary points of inflection. This is where, these are the points where it goes from being concave down to concave up, or vice versa. Okay, so I think that's pretty interesting. Yeah, stationary points of inflection have to be where the first derivative is zero. Okay, so for example, at the very start, this is a stationary point of inflection because the first derivative goes to zero at that point. So that's a stationary point of inflection. And you can see when we graph the second derivative that the concavity changes because the second derivative goes from positive to negative. Okay, I feel like I'm over-explaining, but it's actually a little bit tricky, so it's important you wrap your head around those concepts. All right, let's have a look at the last thing, which is to sort of say, all right, if we're graphing it now, these are all the different scenarios we can have. And I would recommend you sort of maybe take a screenshot or something and stick this in your bound reference. But let's look at the most straightforward situations where this first derivative is zero. So if the first derivative is zero, hopefully by now we realize that that can correspond to a local minimum or a local maximum. But now we can do that second derivative analysis where we can say, all right, is this concave up or is this concave down? Well, this local maximum is concave, and I always forget, it's concave down. It's sort of facing down is how I think about it. So if we go back here, concave down is this way. So the second derivative is less than zero. And similarly here, the second derivative is greater than zero, so this must be a local minimum. So if you're doing the algebra and you realize that the first derivative is zero and the second derivative is less than zero, then you know it's a local maximum. And similarly, if it's greater than zero, the second derivative is greater than zero, you know it's a local minimum. And then from there it gets a little bit more confusing. So let's look at the situation where the second derivative is zero and the first derivative is zero, but you notice there's a condition here, and the concavity changes. So we need, at that point, the concavity to be changing, because otherwise you just have trivial solutions where, you've got your first derivative is zero and your second derivative is zero, but it's not interesting. There's not a change in concavity at those points. So we need this special condition here, because otherwise, it's uninteresting. So if we look at these examples, so these are stationary points of inflection because the concavity changes. If you imagine a tangent line, it would be concave up to this point, and then it would become concave down. It's in the reverse here. So that's the first derivative is zero, and the second derivative is zero. And so we need to investigate what's going on, and it's a stationary point of inflection if the graph looks like that, something like that. Okay, if we look at, the other situations where we have a second derivative being zero, we can get these situations where the second derivative is zero, but the first derivative isn't zero. So we have the concavity changing, but overall it's sloped negatively. So the first derivative is zero, so we have a decreasing curve, but the concavity changes. So these are some funky functions, but yeah, you would be concave down, and then you get to this point, and then you become concave up. And the reverse situation here, the first derivative is greater than zero, so you're on an increasing curve, so the tangent's always positive, but the concavity is changing. So it has this type of feel to it, this type of look. Okay, and then there's the other situations where you've got both the first and second derivatives are negative, so you've got a decreasing curve and it's concave down. If the first derivative is negative and the second is positive, the function is still decreasing because the first derivative is negative, but it's now concave up because the second derivative is positive. Okay, and the other two scenarios obviously as well. First derivative is positive, so the function's increasing, tangents are always positive, but it's concave down. And finally, obviously, the function is increasing and it's concave up because the second derivative is positive. Anyway, I'm probably not explaining it very well, but hopefully that makes some sense. Take some time to really step through those ideas, because if you really understand this, when you're graphing functions, when you just get given them, you can really start to understand what the stationary points look like, and that makes life a lot easier to draw them, because if you know what's a local minimum or a local maximum at some point, you know the behavior around that point. And similarly with these other ones. Yeah, hopefully find that helpful. If you did, give us a thumbs up. Let us know how it's all going. If you need any private tutoring, please reach out. You can find my email address in the description. And good luck. Hope it's all going well, and I'll talk to you soon.